All right, I want to take a look at the concept of variation. We want to look at some models of what's called direct and inverse variation, something that's introduced in Algebra 1. And we're going to go on this. We're going to look at some other types of variation, joint variation, and combining these variations into more complicated relationships. So we have three basic types of variation: direct, inverse, and joint. So direct variation is a simple thing. It can be modeled as y equals kx. So something like this would model k right here is some constant. Okay, so this might model something like the miles traveled by a car when it's driving at a constant rate for some number of hours. So this would be time, x would be time, and y would be the miles traveled, while k would be my constant rate. So that's direct variation. This can come up in a lot of different instances. In a word problem, this would typically be described as something like y varies directly with x or as x. Alternatively, there's another type of variation called inverse variation. I still have y, I still have y equals k, but for inverse variation, y equals k over x. This is modeled in real life by situations such as if you have multiple workers trying to complete one job, say, digging a hole or something like that. More workers causes it to take less time. So I'm dividing by a larger number causes it to take less time. So these are the two basic types of variation: y equals kx, y equals k over x. We will also see that we can manipulate these to say things like y equals kx is also the same as y over x equals k, and y equals k over x is also the same as xy equals k. Now understand, in all of these, when we say k, k represents a constant. It is called the constant of variation, or sometimes the constant of proportionality. So these are two very simple types of variation. We're going to see more complicated forms, starting with what is called joint variation. Joint variation uses three variables, three unknowns. So I might say something like z is equal to kx, y. Again, k being my constant. So z here might represent the money made by a theater, while x is ticket price and y is tickets sold. I have two factors varying that can both influence the amount of money that my theater makes. Now note, this is just a general setup. The variables can be anything. They don't have to be y, x, or even z. And another thing is, as these get more complicated, I will have things like powers of variables or even square roots of variables, and I can combine the variations. And we'll see some examples of that as we go through this. All right, so I want to start slow. We're just going to look at some equations first off, and I want to say, do x and y vary directly or inversely? Some of these are more obvious. I remember that direct variation generally is y equals a constant times x. Inverse variation is y equals a constant over x. So, if I see y equals 4x, somewhat obviously this is direct variation, where my constant of variation, my k, is 4. As I look at more of these, I see some of these are not in a nice form. xy equals 10. Well, again, if you think about manipulating one of these equations, y equals kx, y equals k over x, as I said before, if you move the variables to one side, you could see that this is in fact inverse variation. Another way you could see this very obviously is to solve for y. If you solve for y by dividing both sides by x, then we can see that y is in fact 10 over x, which is an inverse variation with a constant of variation 10. How about this next example? X over y equals 9. So the ratio of x to y is always 9. Now again, solve this how it makes sense to you. If it makes sense to solve for y or for some other variable to tell, that will work. If I multiply both sides by y, I get x equals 9y. And you can tell from there, or if you prefer, you can solve for y by dividing by 9 or multiplying by 1/9. Either way, both of these indicate that there is in fact a direct variation going on here. I have different k's depending on the way I write it. The way I think of is y varying directly as x or is x varying directly as y. But it's clear that this is in fact a direct variation. Lastly, here I see y equals 1 over 3x. It's already solved for y, so I'm going to consider where is the x in relation to that y. Well, y equals, and over here I have something over, it's over 3x, but the x is in the denominator. That x being in the denominator is a good indicator that this is in fact inverse variation, which means I can see that further as 1 over 3x is 1/3 over x. Those are in fact the same thing. So this is in fact inverse variation. Okay. Let's take a look at a few more examples of given equations. I want to describe the variation represented by each equation in words. Now in each of these, k is given to me. In each of the previous examples, there was a given k that I could find. Here, f equals 15a. So what we could say here is f varies directly with a. Let's take a look at b. Z is equal to 3 over the square root of w. Well, z is equal to something over my variable. That indicates inverse variation. So z varies inversely, but it varies inversely with what? Well, not just w, but the square root of w. So notice I made reference before, some of these problems will in fact use powers or radicals. It won't simply be y varies directly as x every time. One last example. P equals 2.4 times mn cubed. Think for a second. I see P equals, there's my constant, mn cubed. I have two things right here. Two things looks like a double direct variation. This is a joint variation. So P varies jointly with m, and you could say n cubed, or typically we might say the cube of n. But this is in fact a joint variation. So a big part of this, the first part of this is understanding what the equations look like before we go into word problems, which will be the main thrust of this. But before we go into the word problems, I want to take one more look, one more thing. Here I've given you some tables, and these tables show a relationship between x and y. We want to determine, is this direct variation, is this inverse variation, or is it in fact neither? Move my paper up just a bit. All right. So direct variation, we know y equals kx, which means, as I said before, that y over x is k. For inverse variation, we know that y is equal to k over x, which implies that x times y is k, is a constant. So if we're given a table of values, we can investigate by checking both of these things. So y over x, let's take a look. Let's make a column here for y over x and see, is this in fact a direct variation? Well, y over x, 16 divided by 4 is 4. 28 divided by 7 is 4. Less obvious, but 52 divided by 13 is also 4. And 72 divided by 18 is in fact 4. So all of these equal 4. All of them match up, which means this is in fact a direct variation. What variation? Specifically, y equals 4x. Let's go ahead and do the same kind of idea with this next table right here. If I try y over x, Now these numbers, mind you, are not very obvious. I see 3.75 and I see 15. 3.75 over 15, I'm going to be lazy and just grab my calculator. 3.75 divided by 15 is 0.25, or 1/4. Next up, I will see 3/8. 3/8 is not 1/4. These don't match up. Next up, I'd have 2 over 6, which is 1/3, and then 0.5 over 1.5 is also 1/3. But these are not all the same. Okay. So then what I would move on to do is check. Well, maybe this is inverse variation. Maybe x times y equals a constant. 15 times 3.75 is 56.25. Well, if I do 3 times 8, clearly I do not get 56.25. I get 24. So those are not the same. So what I see here is this is not a direct variation. This is not an inverse variation. This is, in fact, neither. Because y over x was not the same value for every set of values, and x times y was not the same for every set of values, I can conclude that this is, in fact, neither direct nor inverse. All right. The main idea of variation, what it's most commonly used for, is in dealing with word problems. Some of these can be very simple, and some of them will require a 3-step process. This first one right here is a simple one. The quantity d is inversely proportional to the square of t. You're asked to write an equation to model this variation using k as your constant. So read these carefully. I always read these things all the way through, and then I go back. There's usually a natural way that they're broken apart. The first sentence tells me that d is inversely proportional to the square of t. Read these carefully. So if d is inversely proportional, that means d is equal to, for any kind of variation, I can put in a constant k. Inversely means I need to put something in the denominator. And what's going to go in the denominator? The square of t, so t squared. What were we asked to do? We were asked to write an equation to model this variation using k as the constant of variation. Well, that's exactly what this is. I don't know what k is. I don't have any information to find it. So this is simply my final answer. D is equal to k over t squared for some constant k. Now that's the very simple version of a problem like this. Let's take a look at the full version of a variation word problem. The amount that a spring stretches is directly proportional to the weight of the object attached to it. If a spring is stretched 14 centimeters by a weight of 10 kilograms, how much will it be stretched by a weight of 6 kilograms? So again, there are naturally a few separate parts to this. The first sentence, the amount of the spring stretches is directly proportional to the weight of the object attached to it. So the stretch is directly proportional to the weight. So step 1, my model is S equals KW. Now if I look at the second sentence, I'm told two things. There's a stretch of 14 centimeters for a 10 kilogram weight. And then I am asked, how much will it be stretched by a weight of 6 kilograms? This right in here, that information allows me to do my second step, which is to find K. So, I know S equals KW. There will be a 14 centimeter stretch for a 10 kilogram weight. I can solve then and find that K is 1.4. So what do I know now? I now know my equation is S equals 1.4W. Now some problems might ask you to stop here, but typically there's this third part. In the third part, I'm given another value, or sometimes values if there's more than two variables, and asked to predict the missing value. How much stretch will I have for a weight of 6 kilograms? Well, for a weight of 6 kilograms, this is step 3, put a little 3 right here, S is equal to 1.4 times 3, which is 4.2. Oh, I'm sorry, I wrote kilograms. This is stretch. That's 4.2 centimeters. Please be careful of that. These are word problems, so you will have to pay attention to things like units. There is a 4.2 centimeter stretch for a weight of 6 kilograms. So again, the problem like this told me generally what's my model. Then I had some information I could use to find the value of K. So I came up with more information about my models, more specifically S equals 1.4W. Then I used that model to find another value of S. All right. I'm going to do a couple more here. The quantity P varies jointly with M and the square root of X. If P equals 81 when M is 6 and X is 9, find P when M is 10 and X is 25. So P varies jointly with M and the square root of X. So step 1, P is equal to K, that's what varies means, P varies, jointly with M and the square root of X. So jointly means there's a double direct variation, M and the square root of X. This second bit, P equals 81 when M is 6 and X is 9. I'm going to use that now to determine the value of K. 81 is equal to K times 6 times the square root of 9. Well, if I go ahead and evaluate that, that's 6 times 3. So 81 is equal to 18K. And if I divide, what I get is 9 halves, or 4.5. All right, so now I know my equation is P equals 4.5 M square root X. So find P when M equals 10 and X equals 25. When M equals 10 and X is 25. And there again, I'm putting that parenthesis when I don't need it. So 10 times the square root of 25, that's 10 times 5, which is 50, times 4.5. 4.5 times 10 times 5 is 225. All right, so that will be my answer. P equals 225. So when you're going through these, they're not very complicated. It's just a matter of reading carefully. Make sure you read this carefully. Don't read square root as square or vice versa. And then separate. This is one situation. Find P when M equals 10, X equals 25. That's your last step. Some of these will be a little bit more sciencey. The current in an electrical circuit varies inversely as the amount of resistance in the circuit. The current is 10 amps when the resistance is 24 ohms. Find the current when the resistance is 30 ohms. So, if you want, you can just represent you can represent current as C and resistance as R. Okay, but current varies inversely as resistance. I'm going to go ahead. I know that current is actually supposed to be represented with an I. resistance is just an R. So I equals K over R, because current varies inversely as the amount of resistance. So if the current is 10 amps when the resistance is 24 ohms, what does that tell me? What's K? 10 is equal to K over 24, which means 240 equals K, and I now know that I is in fact 240 over R. So again, step 1, step 2, I now know what K is, so I go to step 3, finding the current for a resistance of 30 ohms. 240 over 30 gives 8 amps. Box that. Alright. Hopefully at this point you're getting the general sense of this. Again, it's just about getting those basic relationships down, using them, reading the questions carefully. I'm going to do one more word problem, and then we'll close this out. S varies directly with the square of P and inversely with Q. Find the equation to represent this relationship if S is 27 when P is -3 and Q is 4. So just reading this, I can tell that this is different than the last problems I did. This is not a three-part problem. S varies directly with the square of P and inversely with Q. Now, this is not two separate equations. This is a combined variation. I need one constant for direct variation right up here. I don't need a separate constant for the next one. I'm just going to consider them as one constant. K, P squared inversely with Q means I need Q in the denominator. So I can see now that S varies. That's what the K is. K is my constant of variation. Varies directly with the square of P and inversely with Q. I want to find an equation to represent the relationship if S is 27 when P is -3 and Q is 4. So I'm going to plug those values in. And what I should find is this will give me the value of K. S is 27 when P is -3. I got to remember to square that. And Q is 4. Okay? So that means 27 is right here. This is 9/4 or 9K over 4. 9/4 K, 9K over 4. How will I solve this? Well, I'll multiply by the reciprocal. 4/9 multiplied to both sides. Here I'll just be left with K. And here 4/9 times 27. 1/9 of 27 is 3. So 4 of those will be 12. And you can double check with a calculator if you'd like. So 12 is the value of K. I was asked to find the equation to represent this relationship. Well, the equation, I know S is KP squared over Q, but I now know that K is in fact just 12. So that's what I'm going to see. This is my equation. Hopefully this makes sense. Again, this shouldn't be too complicated of a topic. Just work hard, read carefully, and you'll get it.